Today we're going to be talking about unlocking on-chain potentials. We got a lot of talented workers and a lot of talented teams here to talk about it. So from the layer 2 side, we're going to be talking about what the platform is doing to facilitate these things. So to get started, Stark's going to look at I'm notorious for giving too much context in these conversations, so I'm going to make it as concise as possible today. At the beginning of time, the Big Bang sprang everything into existence.
And there was the hot nebulous gases that coalesced into planets. I hope this isn't too much context here, sorry. On those planets, there's organisms that figured out how to manage their data and how to secure their data. So we're going to walk through a brief evolution of data security. The most naive way to secure your data is just a flat file. I mean, it's the most naive way. It's also the most efficient way. I'm just going to write it to my disk. I'm going to read it from my disk. It's really fast, and it's the least secure way you could possibly secure data. And you know, people, software engineers, people in our industry, people in Web 2 have dealt with these issues for a long time, so they created database systems. And as database systems propagated, it's still the same issue. You know, if someone walks into a data center with a large magnet, you wipe out everybody's data in the entire data center. So we have redundancy. People need redundancy. And this whole classification of distributed systems and distributed computing and distributed networks came about. So Web 2 now has the same problems. I want this piece of information and I want it to be secure. How do I secure it? Well, I'm going to have it geo-redundant across multiple different data centers across the globe. Now the only problem there, and we have this demarcation line here until we get to what we're all here for, which is blockchain and Web 3, and that is permissionlessness. So we have these gossip networks, these protocols that have clusters, but they're all permissioned. Everyone is whitelisted and access listed in the cluster. Well, that's not ideal, especially for user information that we want propagated for everybody in a trustless manner. So now we have these blockchains. They're beautiful, they're redundant systems. All the computation is re-executed across the entire platform. Every node in the network re-executes the state. If I want to know that a piece of state exists in state today on Bitcoin, all I have to do is go back to Genesis and re-execute every single state header until today. And that's great for user security, but as you can kind of tell, really expensive, not super optimized. There's gotta be a better way. So that leads us to the L1 scaling problem. You know, it's why a lot of people are interested in L2s. You have this block producer, and that block producer is barking out the state. For the time being, we'll disregard consensus. Why can we trust that block producer? But this block producer is barking out a state. The new state is 42. And in the current paradigm, we have all these validators that re-execute the state. So really expensive computation to get everybody on the same worldview of the blockchain today. Well, we don't have to do it that way. We can have the barker, or the block producer, basically take a little more computational steps and generate a proof as he's executing the computation. So now we have the proof and the execution. And across the validator set now, all we have to do is verify the proof. So we have cheap proof verification across all of the validator set with one larger machine, basically taking a few more extra computational steps to generate that proof. So execute once, verify everywhere. And this is the beauty of Stark proofs. So we're starting with Stark proofs. We won't get into the moon math of it all. If you want to go as deep down the rabbit hole, there's plenty of stuff there. You can read Elie Ben Sasson's papers from a decade ago. But as far as intuition goes, these are the graphs that really help me. And these graphs on the right, they're not an actual benchmarking of the system, but they're more to help you with your intuition of why a prover and verifier work well together. So if you look at the top one on the right, you can see X is just the naive execution of the computational state transition. And that's the way that blockchains work today. I have some state transition that was applied by a block producer. I'm going to apply it locally, and I'm going to re-execute. Naive, slow, expensive. Well, with these incredible math primitives, these ZK proofs, in our case, it's a Stark. And I'll say it a couple times, but Stark is scalable, transparent arguments of knowledge. So the scalable really comes in these graphs. And so to give you an intuition, compared to the naive execution that's just up and to the right, we get this logarithm. We get this beautiful logarithm where the more computation we do, it just gets cheaper and cheaper to do it. So we can verify these things in a fraction of the time. And that asymmetry between the naive execution and the verification is really what drives the engine here of scalability. So again, on the bottom right, not an actual performance benchmark of our system, but just more for your intuition. The prover does need to take computational steps to generate this proof. It is slightly more computationally expensive to generate this proof than it is just to execute the transactions in the state change. So we have slightly more steps. It's called quasi-linear. So it's quasi-linear in the number of steps to generate the proof, but then we get this huge ramp up in scalability of the verification costs. But since we're L2, we write our state transitions, we write our proofs to L1, and we get the redundancy of information at L1. So L1 propagates all that information to every node of the network, and we still inherit the security guarantees of the base chain. Okay, so in this way, you can think of validity proofs as kind of a compression of sorts. We are bundling these transactions at layer 2, we're bundling this computation, and we're writing it in a batch proof to layer 1. So in that way, you can think of it like a zip file in the sense that it still keeps the integrity of the underlying information that it's writing to L1. So we're compressing computation at L2. Okay, cool. So that's Starks. The beauty of the asymmetry between the prover and the verifier, that's what brings a lot of people into the ZK system. But why Cairo? So if you've messed with Starks before, and if you mess with things like SIRCOM or SNARKs, you know that you have a circuit. You're proving some statement of computational integrity from a prover to a verifier, such that the verifier understands is convinced that that statement is correct. Well, one of the things that's beautiful about Ethereum and Solidity is this generalization, this expressiveness of Solidity. I can write any business logic I want in Solidity and bring these beautiful applications to life. But that's only possible with a Turing-complete language. So that's what we set out to do and what we've done with Cairo. So Cairo is a Turing-complete programming language that writes provable programs. And you can execute your Cairo program to prove that to an Ethereum smart contract that the result is valid. So if you think back to the last slide, not only is the verifier running in a fraction of the time in a logarithm and using that log scale to speed up verification of these programs, we can also write it in a resource-constrained environment. One of the original ideas and verbiages for the Ethereum platform was that it was going to be the world computer. Well, it ends up having the computational capacity of like a Raspberry Pi, basically. So in order for us to write this verifier, we need to be able to write it in a resource-constrained environment. And that's what we get on the Ethereum L1. So why Cairo? Cairo lets us write generalized computation to L1. Okay, so why Starknet? Cairo is the thing that underlies StarkX, it underlies Starknet. So what is Starknet? Stark, scalable, transparent arguments of knowledge. So we leverage Starks under the hood. It's what we do really well. It's what Eli Ben Sasson has been doing for a long time. We've kind of been a part in the creation of Starks, and that's what we leverage for scalability. No trusted setup. So the T in Starks is for transparent. There's no trusted setup environment. You don't need to trust anybody. Starks come with that out of the box. So it's all about scalability. We're leveraging that prover and verifier asymmetry. And then computational integrity without re-execution. And that's why we're all here. That's what we saw in the previous slides. That's what gives us the scalability that we see today. Proof verification is cheaper than the underlying computation and computational compression. So this is what we bring. This is what we offer with Starknet. Composable, generalized programming in Cairo with cheap computation. I wanted an excuse to put all of the in-bricked NFTs in one. Oh, you can't even see it very well. There's an NFT artist who has made the most horrific NFTs of all of our founders and people. So another reason to use us is because we're a strong team and we fostered a really strong environment here in the community. Okay, so we're talking about unlocking on-chain potential. So what are these Starks and what are these validity rollups? What do they enable people to do that you can't do on Ethereum? So let's talk about recursive proving, one of the unlocks of Starks. Sharp is the shared prover. It's the architecture that writes the proofs and the validity proofs from L2 to L1. And what does that architecture look like? Well, it takes a bunch of Cairo jobs, and it writes it to this off-chain prover. You can think of it kind of like a train station. It's not only a prover, but it's also a job scheduler. So it takes in these jobs, and for a long time, without recursive proofs, none of these trains could leave the station at the same time. Basically, the train is stopped, it's waiting for computational steps to come in until it makes economic sense to prove that computation, and then it writes that computation validity to L1. Without recursion, you have to do it in this very synchronous way. And then yet we're writing to a solidity verifier on L1. So, you see this very static. We get a Cairo job, we run the prover, we send the proof. But with proof recursion, you get more of a tree structure. So now, and the big unlock here is that the solidity verifier is written in solidity. So all we needed to make this recursive proofs happen is a Cairo verifier in Cairo. And once we have that, we can start tiering these computational and provable jobs. So you get this tree structure. So if you look at the top left and the leaves, the train at the station is not waiting to get filled anymore. We can run these smaller batch jobs to prove Cairo code, and then we can prove the proof. And in that way, we have this kind of meta transaction of we can finally batch at the end of this one large recursive proof and prove that proof. And so that opens the door to a lot of different things. These really intensive and computational intensive jobs are resource intensive, and they're also expensive to write to L1. So when we have things like proof recursion, we can run things in parallel, we can spin up spot instances in the cloud. The whole system, the system by and large, gets cheaper for us to run, but it also gets cheaper for the users to run. And at the end of the day, that's what we're bringing. We're trying to bring cheap computation to you guys. Lower latency, so if you think about that tree structure, and you think about where the proof was being generated in the tree structure, well, as far as the first Cairo proof that was proved and the proof that was generated, that finality can be said to be had there at the very top left of the tree. Instead of waiting for the train to fill up and proving everything in one fell swoop, now we have finality at some of the leaves in the tree. All right, so one of the cool things about StarkWare, and one of the things that I love, is that we don't kind of make announcements of announcements. So when we announced proof recursion, we announced it on the day that it went live in the production. So we've seen max latency reduced by 25%, gas cost reduction of 35%, off-chain cost reduction of 65%. And we're bringing those cost savings not only to the development community, but to the users. Everyone that's using the system gets to see these benefits. Okay, so if you think back to the tree structure, the thing that opened up the door to recursive proofs was a Cairo verifier, an audited and well-run Cairo verifier. So that also opens the door to fractal scaling. The way that we've talked about right now is that we're executing computational proofs at L2 and writing those proofs to a solidity verifier on L1. So if we have a Cairo verifier, now you can take everything we've just talked about and move it up a level. And now we have computational proofs being run at L3 and being verified in Cairo at L2. So not only does recursion make things cheaper for everybody to run, but it also opens the door for fractal scaling. Not every app that comes to an L2 solution is going to need composability. Some will, and it's great at Ethereum L1 and it's great at Starknet L2, but some have different concerns and different trade-offs that they're looking for. So maybe an app is looking for privacy concerns. Maybe they're looking for a really high TPS. Maybe they're looking for composability needs, on and offboarding costs, fee congestion, to make it customizable. So as you're weighing these things against composability, there's going to be a lot of app architectures that need various different custom configs. And that's what this fractal scaling opens the door for. So to review, we have Ethereum L1, very security driven. The security is very high and it's very decentralized. Those two things play hand in hand, but the scale is not there. When we originally came out with StarkX instances, you get a lot of what I'm talking about. It's an application specific rollup. The state change is done at the application layer and at the application specific layer, and it's proved in Cairo. but it's specific to that application-specific rollup. So you have scale, and these are instances like immutable X, so rare, DYDX, names you've probably heard of. So you get the crazy scale, but it's not permissionless, it's permissioned, and it's not composable, and it's not general purpose. So this kind of ushers in the need for Starknet L2, the public L2. Anyone that needs composability, general purposeness, permissionless, the same things you love about Ethereum L1, that's what we have at this L2 layer. And it's fostered this incredible community that you see today, a lot of people sponsoring and a lot of people talks you'll see in a little bit. But we're talking about fractal scaling. So eventually you'll see these app instances that we're writing their state transition to L1. Well, we can write it L3 now because we have a Cairo verifier that can verify the validity of the computation. So now we have control, privacy, hyper-scalability, your ability to customize your app-specific rollup at L3. And one thing that's really interesting is privacy. When people hear ZK and zero-knowledge proofs, they think about privacy because at the end of the day, you've probably heard, it is the prover's ability to prove to a verifier that a statement of computational integrity is correct and valid without divulging any of the information. So that lends itself to privacy. But for us, we write the entire state transition to L1 as the data availability layer. So everything that you do on Starknet L2 is public. And now we can incorporate some of these cool ZK primitives like privacy at L3. So the world might start to look a little different in our landscape. So you might have Ethereum at the L1, the public Starknet at L2, and all of these customizable specific app layers at L3. Use cases up here in this kind of paradigm shift: hyperscaling, high frequency trading of perps and spot, reduced on and offboarding costs, customization for you guys at the app layer, congestion fees, deterministic costs, whitelisted L2 access, custom DA patterns. That's another really interesting one. I don't know if you guys have heard of volitions, but there's basically a hybrid data availability solution that you'll be able to utilize in the Starknet ecosystem. Compute, so you can offload compute-intensive work and prove game state. Gaming has kind of been flourishing on Starknet, and you can think of it almost like a state channel where we can prove game state at these layer 3s to public layer 2. And privacy, like we talked about. I've talked to a couple different people this week who are just really interested in ZK for the privacy. So make ZK KYC statements at this layer 3. Okay. Account abstraction, you'll hear a better talk about account abstraction by Julian from Argent. But just to give you the high level, we have these EOAs at Ethereum, and they're hard coded, and the EOAs are treated as a first-class citizen, right? So it's a public-private key pair that's the first-class citizen. If you want to have any abstract logic that is a smart wallet or a smart account, you basically have to wrangle the Solidity code to make it work with a multi-sig or a multi-call. These things aren't really supported by the L1. What we have on Starknet is we have Starknet accounts as smart wallets. So every single account on Starknet is a contract. So you can operate any business logic you want in that smart contract, and it's a first-class citizen. So you have account abstraction baked in at the base layer. And again, you'll hear a better talk than that later today. But it's going to lead to better wallet UX, so alternate signing curves. We have a signing curve that's baked into L2 that plays nicely with Starks. We need it to operate efficiently within the Stark proofs. So that signing curve is not SEP 256K1 like it is on Ethereum. So let's say we want to incorporate it and we want to have interop. Well, you can with this account abstraction. We can have accounts that implement both signing curves. Social recovery wallets. I eventually want to be able to hand a wallet to my grandma and not worry that she's going to lose her life savings. Argent and Bravos and some other people have incorporated guardians and the social recovery layer that gives you some more options for recovery. Session keys for gaming, automated fraud monitoring, spending limits for on-the-go keys, multi-calls, multi-sigs, paymasters, all of this stuff incorporated out of the box because the protocol supports account abstraction. Some of the things we talk about is mobile signing. You know, it's kind of a surprise that with every single one of you has a trusted execution environment in your wallet, in your pocket right now. But really, they're not really used for signing for public-private key pair generation. So why is that? We think that it's because, you know, account abstraction isn't really baked into the base layer, and so these things are a lot harder to do, a lot harder to bring to life in these other chains. So yeah, you have a trusted execution environment that we can generate private keys and even use hardware accelerated transaction signatures. This is going to be the future in my opinion. Storage proofs. All of these things unlocked by the computational compression that we talked about. Storage proofs, you know, all of these blockchains are just databases at the end of the day. So storage proofs let us prove something about the data set. And you might think, things like Herodotus basically proves things about the layer 1 state on layer 2. So you might think, well, why do we need that? We're proving things about layer 2 to layer 1. Why do we need to prove things about layer 1 on layer 2? It opens the door to a lot of interesting use cases. It removes the need for messaging, so we have this async messaging from L2 to L1 so that we know what smart contracts are doing on L2. We can deposit, withdraw. Well, if we can prove things about the storage layout of L1, then we actually don't need to go through that asynchronous messaging queue. Cross-chain data access. Governance is a really interesting thing. So I can vote based on my L1 assets without moving them or bridging them to L2. I can basically just prove that I am the owner of them on L1. Storage proofs really open up the world to a lot of interesting stuff. Identity attestation, similar concept. Prove that I have soul-bound tokens or NFTs at L1 without bridging them up. I can still make strong security guarantees via the storage proofs on L2. And then account abstraction. Trustless bridging. So we talked about this asynchronous messaging queue. And really, if you have this modular design of the L2 sitting above the L1, you really need a robust messaging queue for smart contracts to talk to each other to and from L1. So this is what it looks like. I'm not going to get too technical here, but basically we have the ability to not only bridge data from L2 to L1, not only bridge assets from L2 to L1, but also data. So we don't make any assumptions about the data that you're passing. All we do is give you the messaging protocol, and you can use it as however you like. So what does that open the door for? Since we're talking natively, L1 only needs to know that the proof of execution at L2 is valid. It can trust all of the messages that are coming to it. So Ethereum has certainty of what happened on Starknet. Ethereum has mathematical proof that a message was sent, and then a minimal message delay. So in order to block against some type of reorg, we're going to wait for 10 confirmations for that message to be considered final. And no element of trust in the mechanism. So we've all heard countless bridges that are run by a multisig in some entity, and that multisig is actually 5 of 8, and 5 of the keys are one entity. In this paradigm, you don't need to trust any of that. All you need to do is trust that the math that's underlying all of this is executing correctly, and that these validity proofs are being proved as valid to L1. Interesting use cases here, in my opinion, are the message passing. So fact registries give us the ability to prove to L1 about a fact at L2. It's actually the underlying engine that makes Starknet run. But you guys can use them too. Cairo code can be proved outside of the execution context of Starknet. So you can come up with these interesting data models where the example that's given in the Cairo documentation is interesting. You basically can have a Sudoku key, and the Sudoku key can prove that the Sudoku was done correctly, and you prove that fact to L1. And now I can have a Solidity smart contract that checks the fact that that Sudoku puzzle was solved correctly and make some type of business decision based on it. So I can reward you for doing a Sudoku correctly without ever actually showing the key to anybody publicly. Remote controlled contracts, so I can control L1 contracts based on information passing from L2 to L1. Let's say that I have a Solidity contract on L1 that's managing an ENS name. I can actually do that in a computationally optimized layer at layer 2, but just send information passing via messaging to L1. And then custom protocols. We make no assumption about your payload size, what's in your payload. You guys define the bridging protocol, and you can run it all in validity proofs. Decentralization, I think I'm running a little low on time. So we'll just kind of speed run through this. Sequencer, we're basically in the process of open sourcing all of our code. You guys might have seen that we announced that we're open sourcing the prover, and we're rewriting almost everything in Rust. So the sequencer, we have a module called the blockifier that we just open sourced. Feel free to check out our GitHub. Full nodes, we have full nodes in Papyrus, Pathfinder, and Juno. Juno is actually an initiative by Nethermind, who's here today. If you're interested in full nodes, feel free to reach out to them. And then what's in progress is the P2P layer. So we want to sever the connection to a centralized API provider. And then the prover, like I mentioned. This is a big one for us. It's going to be open source soon. Keep an eye out for that. Verifier is written in Solidity. Go check it out on Etherscan. Starknet Foundation. So the goal of Starknet Foundation is to make Starknet a public good. It's a not-for-profit created in November 2022. Eventually, this will control all the protocol changes. And then if you are a Stark holder, you'll be able to either delegate or vote based on your Stark, your Stark tokens on protocol changes. And then off-chain signal voting with Snapshot. Okay. So, some other interesting things that kind of Starknet, Cairo, Starks, all the things we talked about today unlock, and that we're doing, including with a couple people here like Danilo and Paul. Substrate sequencer, writing a sequencer in Substrate, utilizing tooling in other communities. Tendermint sequencer, L2 light clients, Beerus, well what, let's go. Rust, so there's certain rewrites being done by Lambda class. Like the Cairo VM is being rewritten in Rust, we're seeing a 50x speed up there. Cairo to LLVM, so let's say you want to make sure that there's a good execution in LLVM, but you don't necessarily want to generate an entire computationally expensive proof. We're seeing 25,000 x speed up there, which is a funny number. Parallel transaction execution, on-chain AI, you get the point. There's really fun things happening. The future is bright. If you're not already in the ecosystem, we'd love to have you, and thank you for your time. Enjoy the rest of the day.